told you that every biological process in the human body could be simulated via a simple computer model, a video game, if you will, defined by no more than a handful of simple rules. Impossible? Yes. But what if we lowered that bar? Could we model the behaviour of just a single cell type? And could we use this model, this game, to influence how we engineer cells, tissue, and even organs in a laboratory? In this talk, I'm going to explain how the Vascular Structure and Function Research Group are attempting just that. We'll also take a peek behind the wizard's curtain to show you some of the code that drives our computational models. I'm scientist and thinker Dr. David Hardman, and this is my VSFRG talk. Let me take you back to 2019, when we took the outside world for granted. We laughed at fools stockpiling for Brexit, and irresponsible use of toilet paper was rife. A collaboration of bioengineers from around Europe formed with the ambitious goal of creating innovated and vascularized muscle on a chip. Researchers from the Institut Curie in Paris began designing a three-dimensional cell co-culturing environment, while researchers in Institute of Molecular Medicine in Lisbon began defining a protocol for growing muscle tissue from stem cells and co-culturing muscle cells with neurons and endothelial cells. The number of variables required for co-culturing cells so consistently to produce good quality muscle tissue means that finding the optimum conditions by trial and error alone would be extremely expensive and time-consuming. And so the VSFG were called upon to provide computational modelling to fill the gaps in experimental knowledge. Computer models which are properly calibrated and verified are a fast and inexpensive method for testing experimental protocols. Working with live imaging data of cells, we hope that our model will help to predict the optimal experimental conditions for growing muscle tissue. Computational modelling can take many forms. Here we are using agent-based modelling. In agent-based models, the behavior of individuals in a system is simulated by a set of simple rules. These individuals are the agents. Agents could be people, viruses, French people, or any part which makes up a complex system. As these simple agents interact with each other, more complex behaviors emerge, and so simple models have the potential to mimic more complicated systems. So, the myochip project is all about making muscle. But how do we build muscle? You're probably thinking, hitting the gym to pump some iron, but I'm talking about what's happening on a cellular level. Well, it all starts with satellite cells. These are the precursors to muscle tissue. When new muscle needs building, they differentiate into mobile myoblasts. These myoblasts fuse together to make myotubes, long cells with multiple nuclei. Myotubes grow as more cells fuse together. They mature and lengthen to make muscle fibers. Mature muscle fibers are much more complex than this, containing triads of tubules and sarcoplasmic reticulum. But in terms of bioengineering, it is the first stages of muscle fiber growth which are crucial. If myotube production is successful, then the muscle fibers should continue to mature on their own. Myoblasts will therefore be the agents in our agent-based model, and we will study the rate at which they fuse together to form myotubes. As with any biological process, the underlying mechanisms of myoblast fusion are extremely complex. Our task in creating a model is to group cell behaviors into generalized actions which do not require the input of the complex mechanisms going on beneath the surface, but which can still describe the general behavior of the cells. For myoblasts, these general behaviors are: number 1, proliferation. From time to time, cells will divide. From live images we have studied from the Institute of Molecular Medicine, myoblasts remain static for around about 20 to 30 minutes while they divide, after which the daughter or son cells migrate in opposite directions, which brings us to number 2, migration. In reality, myoblasts extend legs called pseudopodia, which they use to pull themselves around their environment. On a larger scale, we can model motion more simply by allowing the cells to move within a range of speeds and change their angle of motion after each time step. The speed of migration and angle of motion have been taken from cell tracking studies carried out on live images of myoblast cells. Number 3, fusion. Our studies of myoblast motion and rate of fusion indicate that there is a negative correlation between the speed of myoblast migration and the rate of fusion into myotubes. This shows that slower moving myoblasts have a greater chance of fusing than their faster moving brothers or sisters. Our hypothesis is that fusion events can be modeled using a simple residence time model in which if a cell spends too long in close proximity to another cell, it will fuse to create or enlarge a myotube. We therefore assume that myoblasts, much like customers in Asda, move in random directions and refuse to practice social distancing. We are creating our agent-based model using NetLogo. NetLogo is a free-to-download resource which uses its own programming language. NetLogese may be a little different to languages you have used before, but I'm sure you'll pick it up quickly. You're now ready to follow the live online Show Me Your Code session. Please feel free to ask simple and non-critical questions along the way. Hope to see you soon. Bye-bye.